way you would hear sounds. So one of the things that I did was I took off the sort of higher frequencies of the wind sounds and any other sounds in the world, because those would not, because the density is different in the air, those would not travel as far. So they kind of attenuate at the higher ends, and you mostly just hear the low ends of sound. Um, there's a couple of other things that I couldn't really account for easily, but that was sort of the easiest one to mimic. And what was interesting about that is the Perseverance mission was the first time that we got sound captured on Mars. And when we made the world, they hadn't captured and sent back any sounds yet. So I was really just going off of the explanations of the science behind the sound. But what was kind of neat is that what we ended up getting was pretty similar off of to what the actual sounds were that were captured. And I later made a drum and bass remix of the world music that samples the real sounds of Mars. And that's not in this world, but it is
Nice.
it is available.
That's
Yeah.
awesome.
Um,
That's freaking great.
yeah, and it's got some samples of like the landing and stuff. So it
You
was
made
kind of
like an
fun.
actual new genre, like
Yeah,
space
drum and
techno.
space.
Let's
Drum and
go
space.
drum in space.
Yeah,
Go
that's
Mars
what I called
D&D.
it. Yeah.
Oh Lord.
Uh, pretty nerdy. So yeah, that was my contribution.
Do we want to
Awesome.
walk over to
For-
the other section, Kevin, or would you like to talk here?
Yeah, well, we can just preface that if we walk over, it'll trigger something very
Yeah.
specific. Yeah.
Okay,
That
everyone
might be
walk
the way
towards
to do
the
it.
other
So
helicopter.
walk towards the other Ingenuity.
Okay. Ah,
And
okay.
here
That's
is
awesome.
my little creation over here, Sophia 1. So Dylan used a very salient word for the world of edutainment, and I thought a lot about like how do we bring levity to this experience as well. It's educational, but that doesn't necessarily mean it doesn't have to be fun in some way. So that little robot that you just saw. So if you go back and then you come back forward again, it'll trigger Sophia again. But I just thought about how about a companion on this planet? How can we make a virtual companion that would guide you through the experience? And the fun fact behind Sophia 1 is that she is all made in VR with VR tools, animated in VR. That actually applies to my own avatar as well as Scouts. So we're very passionate about this space. And Sophia will probably be appearing in other parts of the planet as well, but that is her first little iteration and introduction. I also did a lot of the graphic design as well in general, because in the real world, that's my bread and butter is doing design. So these little prompts that will come up, as well as some of the exhibit design. We really wanted something that felt like a science museum without being too intrusive, which is why, and John will speak to this too, is why a lot of this has triggers on them. So it really feels as if, Scout, I feel like you had a really good description for why you wanted it to be more of a clean slate,
Yeah.
wasn't it?
Yeah, I was really hoping that in designing this world that we could build it as basically if people want to just come here and chill and they don't want to have a bunch of things around them, they just kind of want to experience sitting on Mars and enjoying the sand blowing and that kind of stuff. We wanted to make sure that was possible. But we also wanted to like have a bit of joy of discovery with kind of wandering around and having this exhibit just kind of pop up. There's also a way to activate it from the rover. So kind of both ways, just hoping that people will find it on their own and then kind of come over here and check it out. And then from here, use the map to navigate around, and we'll take you on a little journey in a few minutes here after John has a chance to talk. So, but yeah, we really wanted it to be kind of both the best of both worlds, basically a chill world and an educational world that's really fun. So that was kind of our design idea. Yeah.
And that kind of comes from our backgrounds in so like for instance, I'm a researcher and designer in doing a PhD in learning sciences, and my focus is on designing for immersive learning. So that's kind of what we're bringing to this is this idea of like how can we actually be in the immersive environment and embed the learning within it rather than having it sort of delivered in an instructional kind of way.
Then this is a perfect little
Sean's
project
next,
for
yeah.
you then.
Yeah.
For sure, right?
Exactly.
Yeah.
A perfect
Yeah,
event for
tell
that.
us about. So
Yeah,
everybody,
my background
listen to John.
was in astrophysics and programming. So building a world around Mars was very intriguing to me. And what I brought in was a lot of the user interaction that happens. But the first thing I wanted, while we were building this, we felt a lot of love for Perseverance, especially, feeling like, oh no, Perseverance is all alone on Mars. And so we wanted to track like how long is Perseverance is Perseverance there? So we put a counter. Perseverance has been there for 139 days. But that's our time. What about the perception of Perseverance? How many days and nights has Perseverance gone through? Well, Mars rotates at a different rate from Earth, so it only has been 135 days and nights for Perseverance. So we want both timers in there so that way you have the perspective of what it's like to be on Mars and how there's these little differences. Dylan and Scout put in this wonderful information about Mars and Perseverance that you can come and you can actually look at. And further ideas is to put in more information as more information comes up as well, and more pictures from Mars and Perseverance.
Absolutely. And do you want
Did I miss
to?
anything?
No, I think that's great.
Yep.
Do you want to talk, John, about anything about the rovers, or would you like to wait till we get over there?
Oh, I think we'll wait till we get to the rovers to talk
Okay,
about
well maybe we should
those.
go to the
Yeah.
rovers then. So everyone, in order to navigate
Oh,
over
wait,
to
wait.
the
Before
racing.
before we go there, we should show this
Oh.
little area.
Oh, right.
Oh, geez.
Oh, right.
Okay, yeah.
Right.
Yeah, okay.
So, big thank you to some of the people who have helped us create this world, like Kurotori, who we used their base for the cart system.
Yeah, these are the prefabs that we used. So the Kuratori
PRC
system.
prefabs. Woo!
Yeah.
Yeah.
Yay, prefabs.
Woohoo!
Wow, that's familiar.
And oh, Scout, you didn't talk about the fog.
Yeah, I can really quickly touch upon how I did this blowing sand. So I was using the Sky Probe fog from Silent, and it's an amazing asset. But what was really awesome about it was that I was able to change the settings enough to make it feel more like sand instead of fog. And I feel like it's one of the things that really sells this world. If I didn't have that blowing sand, it doesn't feel nearly as alive. And so I was really grateful to be able to work with that asset. And I highly recommend it if you're looking for a performant fog or sand for your own world. It was really great to work with. So yeah, that was one of the highlights, was kind of getting that in there and feeling like, yeah, it's actually like we're on Mars. You know, we got some stuff happening even if you're just chilling out. So and
Cool.
to briefly mention, this is a silly avatar I made. I put it in here because I thought we might as well have aliens. So if anyone needs a hand puppet that's basically like an octopus alien, you're welcome. Yeah, and
Obligatory Mars
someone has got it
alien.
on. There we go.
Aliens,
Yay! So
aliens
yeah,
and robots.
Martians are
silly
more.
avatar.
Of course, Zen's the one who grabs it.
There we
So what I would,
Now you have a
what I would
puppet.
and hung.
suggest,
Later.
what I would suggest
Should
before
we
we
jump
go
over?
check out like the
Oh, yeah.
the Mars carts, the rover carts, I
Mhm.
think actually we should
Mhm.
probably save that at the end. I think that'd be something really cool.
Oh, good idea.
Yeah.
And
Oh,
then,
okay.
yeah. And
Clever.
I think honestly we should jump straight to
tease.
Jackie if we can.
Yeah, let's do it. We're
Okay,
ready.
sure.
Okay.
Yeah.
Okay.
Sure.
I think saving that for last, I think, is a pretty cool thing.
Good idea.
Yeah,
I think
that's a good
also
idea.
I love
Jackie
it.
would get a
That'll
kick
be a
out of it
treat
because
for
it
waiting.
would be a treat, exactly. So
Which
we
already
can,
having
where would
Jackie
you
here is a
prefer to
treat.
do this at, Jackie? You get to choose. You can go over there
Stand
by
by
the
the
rover
rover?
right there, or by the
I don't
information.
know.
Yeah, we
Well,
can stand by
okay,
the
so
rover.
I
all
just
with the
wanted to
driving
point
gear.
out some things over here that I noticed real quick that I thought were cool.
Oh, please.
Wait, I should introduce
Okay.
myself first. And I'm just warning you all, I'm sorry if this is not like the most high fidelity presentation you've ever been to. I did not prepare slides, so we're gonna wing it, but I think that's a fun way of doing presentations. Okay,
No,
so
informal's fine.
I'm Jackie. I have been operating spacecraft for like 6 years basically. Since I was like 20, and now here I am. I work on the Perseverance rover, specifically on the engineering camera team. So I'm responsible for sequencing a lot of the images that we take of Mars. And before I worked on Perseverance, I also worked on the Curiosity rover on the same type of cameras. Yeah, and also a disclaimer before I go any further. All opinions expressed in this presentation are my own, and yeah, I'm just representing myself in this capacity of this presentation, but yeah. Okay, so a couple of things I noticed over here that I just wanted to point out real quick.
Tracking a little bit. You're tracking us up and tip. I got you.
Okay, here we go. Okay, so this photo, I think it's actually 90 degrees out of rotation.
Sorry.
No worries. Sometimes they get uploaded in the wrong orientation. This is a Mastcam Z image of the SuperCam calibration target. And so this has a bunch of known chemical signatures of various materials. And the SuperCam can fire its laser, which is called the LIBS, at the targets. And it provides a known chemical signature back to the spectrometer, which enables them to calibrate the instrument when looking at real rocks. So you can actually see in this pot, for instance, there's a mark in the center, and that actually comes from the LIBS laser itself. There's also one in here and one on the top one. But yeah, it really shows the new functionality of the mast camera is its zoom capability. Because before it had a fixed zoom. And so now we're able to get much higher resolution, even though we have the same sensor inside of that camera as on the Curiosity rover. Now this photo, I need to look at the file name to be sure, but I'm pretty sure I sequenced this photo. So there you go. And this photo, this was right after we dropped the belly pan off. And what that is on the ground is basically when we landed, we had a panel underneath the rover, and it protects the sample handling assembly, the SHA of the rover, during the forces of landing, and keeps the dust out, you know. And to actually use the assembly needs to be removed. And so from the landing site, we drove to a suitable location, and it actually uses a pyro device, which sounds very dramatic, like a pyrotechnic blowing something off of the rover. But if you see it in real life, it's pretty tame. It just goes pop, because it cuts a little bolt, and then when the bolt is cut, the thing just falls right off. And then you can see the tire tracks, or the rover tracks rather, because they're not really tires, they're wheels, where we backed up. And then once we backed up, this image is taken by the navigation cameras. And I'm a little disappointed in how it came out. I think we did a retake of this one because you can see on this very clean inner part of the belly panel, this was facing towards the inside of the rover. It saturated the detector. And the way this photo is taken is it's actually taken in 16 parts, 4x4 grid, basically going down. And yeah, another thing that you might notice is like there's a little bit of schmutz. That is an official technical term, of course.
I feel like they came
over here on this part of the panel.
Schmutz.
That was interesting. I don't remember what the result of those observations were about what that was. So I'm not going to speak to it, but it was interesting to see that. Similarly, on the helicopter itself, there was some dust on the solar panel. And that dust likely ingressed through the debris shield during landing. And luckily, it didn't really affect the ability of the solar panel to charge up the helicopter's battery. But it's just interesting how those things happen. And actually, so just another point about this, we kept backing up from this point and dropped off the debris shield as well. So we littered on Mars, and now there's these two panels of the rover very neatly lined up next to each other, sort of close to the landing site. And it looks very odd because they're just sitting there in the middle of like this Mars environment. And now we're many hundreds of meters away from that too. So when the sample return mission comes, it's going to land fairly close to our own landing site. And so we might get a chance to image those lonely panels again. Okay.
I have bad news for you. That's going to be a $500 fine each.
For littering, yeah.
The
So
Martian.
this one,
police.
this was a touchdown FHAS, or front HAS cam rather. And the reason why it looks the way it does is because, well, first of all, it's a thumbnail, so it's thumbnail quality, or maybe a little bit better than thumbnail quality. I don't quite remember. And it has the dust cover on it, which creates this crazy black bar. I don't want to call it a vignette, but it's like, you know, surrounding it. It's because you might be able to see it on the rover model over there. It has a dust cover that's clear, so we can at least see through it a little bit. And once we land, one of the first things we do is, again, fire a pyro, and that thing flies up, and we're able to operate our cameras as normal. Another interesting thing about that one is there's two things going on at the top here. There's the dust cover itself, and then there's the lens cover. For a variety of reasons, which I won't get into here, all of our engineering cameras have covers, sunshades over the top of them. So yeah, there's a little bit of sunshade, which you may have noticed if you like looking at our images that we make public on the web. And that's what that is. It's a little metal piece that fits over the top of the camera like a hat. So our cameras have hats. Just another thing that I noticed.
Fancy.
Yeah, so a day on Mars is 24 hours and 37 minutes compared to a day on Earth. And instead of doing a clock that has 24 hours and 37 minutes on it, that wouldn't look very good, you know, from a watch perspective. We changed the length of a second on Mars. So these second counters, if you pay close attention, don't line up. Which if you have OCD might be really, really annoying.
Yeah.
And a lot of memes have been made about, give me 5 seconds. Do you mean Earth seconds or Mars seconds? What are we talking about here?
I'd be sure to program that in, actually.
New York second is totally different.
So in general, you know, if there's any programmers in the crowd, if you've ever had to program time zones, you might be familiar with what a nightmare it is to deal with time zones. The unique difficulty that we have to deal with programming at my job is whether we're working with Mars time or Earth time and converting between the two. Because, okay, this might be too technical of a detail for me to say in a public, I don't think it matters actually. So we have SCLOC, which is spacecraft clock. When the spacecraft is assembled, it has a internal clock that gets turned on actually well before it launches. That's basically starts counting from 0 at its first power on and continues going to the end of the mission. And that provides you with a unique time code for everything that happens on the rover. Then we have LMST, which is local mean solar time. And that is this time right here. So it's just the local time on Mars. And to make things even more complicated, there's LTST, which is local true solar time, which is based on calibrating the sun azimuth to, you know, have the sun directly overhead at local noon. But anyways. Then there's spacecraft event time, which is an Earth time that we can tie to things that happen to the rover on Mars. And then we have, and so on and so forth. So you can understand, like, it gets pretty crazy. Time, what does it mean? Okay, so, but if you're actually operating a rover, what are we doing? Okay, number one question I get asked like all the time, and like I don't blame anybody for asking this question because I think it's a really common misconception. Usually the conversation goes something like this, like, oh, you like operate the rover? That's pretty crazy. So what's the one-way light time? And I'm like, well, you know, it depends on the time of the Mars year, you know, distance between Mars and Earth. But usually it's about, you know, 15 minutes one way. And then they're like, wow, so that's a pretty bad delay if you're like joysticking it, you know, right? And I'm like, oh, honey. So, where I actually just came from, a little before this presentation, I got off work at 5:45 my time and popped into this world at 6:30. We were planning Sol 136 on Mars. So the commands are sent in a batch called a bundle, all at once, for each Mars day. And sometimes we do a couple days at a time because everybody needs a break, you know. And also consider the consequences of having these two different sets of time. Over time, you accumulate an error. We've been on Mars for 135 and a half days, and that accounts for 139 days on Earth. Early on in the mission, I was living on Mars time, where, you know, the time that I started work moved forward by about a half an hour every day. In actual practice, it was much more chaotic than that, where things could move 3 hours one day to the next. But what it enables us to do is to operate the rover every single day. Because when you send the commands, you need to get the data back to be able to plan the next thing. You don't want to drive when you don't know where you're at. So you need the images to be able to drive. And the images only come down at discrete time. So, realistically, sometimes we have to take a day off. And we give that a fun name. It's called a soliday. Unfortunately, we don't get the day off from work on a soliday. Yeah, so Sol 136 is coming up. And basically, you know, when we send the bundle, you know, they basically package up the set of commands that we're going to send to the rover. goes to a guy called the Ace, and he works in the dark room of JPL. And there's actually a world in VRChat that models that dark room, and also like the surface of Mars with the rover and whatnot. And that is the control station for the Deep Space Network, which is how we communicate with any spacecraft past low Earth orbit. And so what's really cool about that is like they make it look really cool. I'll just say that. And so yeah, the Deep Space Network sends our commands up, and then it runs, and we have satellites orbiting around Mars. And when we take our data, we shoot that data up to those satellites, and then they send it back to Earth, and you get to look at pretty pictures. So I think it's a pretty good deal. And the most amazing part about that is that it's, an international effort. It's not all NASA assets. So we partner with ESA, not just on the orbiters, but also, many of our instruments were developed by nations in the European Union and are operated by nations in the European Union. So when we do our operations, we're communicating with people all around the world every single day, which I think is really cool that we get to do that. Okay, so I'm going to take you over to the rover, and I'll give you a brief tour of what's going on the rover.
Heck yeah.
Imagine experiencing lag for 15 minutes.
Oh, that's how they get around it, is they just send up that batch file, call it a day.
I know.
Yeah.
Yeah, there you go.
On Mars, Perseverance will get you
Also,
anywhere.
you have a really
That's
big
fun.
avatar.
I like that.
Read your DM.
Okay, so yeah. Where to start? I guess egotistically, the cameras that I operate, because why not? So right here we have the front has cams, and there's 4 of them. All of our cameras are in pairs because we take stereo images. And this isn't just because we like to wear those red and cyan 3D glasses like we're in the 90s. Although we do that. They have plenty of those around the office. It's because stereo data is extremely important to how we do operations. Nowadays, with self-driving cars, they use, LiDAR and machine learning and a number of techniques to generate a 3D understanding of their environment. But we've been doing this since the 1970s, and so the technique that we use is much older and more mature. And it involves using a set of stereo cameras, and you're able to generate a 3D model from 2 images. And a very sophisticated knowledge of the geometric parameters of those cameras. I do not want to bore you with all of that, but I totally could talk about that for an hour. Anyways, so that accounts for 2, right? Well, now there's 4. And inside the rover, there's 2 CPUs. And we don't call them CPUs, we call them RCEs, Rover Compute Elements. And they're very, very slow. It's about the equivalent of processing power of like a Power Mac G4 from the 2000s, which is, it's not exactly that processor, but similar scale. And I'm imagining some of you in this audience are younger than that processor. So, yeah, and actually, I mentioned earlier the dust cover. That's the dust cover right there. Okay, so that's the HazCam. We have 2 RCEs, and when we switch between them, we switch between the pair of HazCams that we're using. On the Curiosity rover, we had two sets of all of our engineering cameras. And then they realized maybe that's not as necessary as we thought, but hedge our bets. That's not exactly the rationale, but it makes for a nice story. Anyways, okay, so up here on the outer edge, these two guys are the navigation cameras. And these have a 90-degree field of view. By the way, those ones down there have a 130-degree field of view. It's like a fisheye lens. They're 20 megapixel cameras. All of these cameras, the engineering cameras, are 20 megapixel. And then over here, these two are the Mastcam zoom cameras. And unlike the engineering cameras, they're not perfect copies of each other. They have slightly different focal lengths, and that enables one to zoom in further than the other. And up here is the SuperCam, which is a spectrometer. If you're not familiar with what a spectrometer is, it is a special type of camera that can measure infrared spectrum in addition to visible spectrum, and some spectrometers even measure UV. Or at least this type of spectrometer. There's also X-ray spectrometers and so on and so forth. The cool part about it is that it also has a laser. A very powerful laser, which is capable of blasting the surface of rocks and vaporizing a small portion of that rock. And the vapor that comes up can be captured in that moment by the spectrometer. And you can read chemical signatures off of that. So that's what SuperCam does. It enables us to study the chemical composition of rocks, and not just rocks that are right next to us. It can be rocks that are further away. It works best with a laser, but we also take observations from much farther away. It also has a very narrow field of view camera called the RMI, the Remote Microscope Imager. And that gives us a little window into whatever we want to look at. Sometimes it looks way off in the distance, and it can see even higher resolution than the Mastcam on like a not like the sensor is a higher resolution, but it can just see, like, you know, because it because of the way the lens works. But anyways, sorry, I'm struggling with the exact technical wording, and I don't want to say like something super wrong. Okay, so over here we have our turret. This is called the turret. It's the end of the arm, and it's a big boy this time around. People were talking about how large the Curiosity rover turret was compared to Spirit and Opportunity, and this one is much bigger than Curiosity. It's so large, in fact, you may have noticed back here there's a big truss. This truss, as a fun fact, is there, and it wasn't on Curiosity, if you pay close attention between the two rover models. When the arm moves around, the torsion forces induced by the heavy turret actually introduce undue stress on the rover chassis. And so this truss is here to help to mitigate some of those forces. And it also provides us a convenient place to put the chip that has all the names that we sent to Mars. So if you sent your name to Mars, there you go, it's right there. So yeah, back to the turret. Okay. This is our do everything for touching, sniffing, blowing on things, or even taking core samples. So right here, I'll start with this guy is the Pixel hexapod. Pixel is an X-ray spectrometer, and that's what I mean by sniffing. It's not literally sniffing, but if you bring it very close to a rock and observe that rock over a long period of time, the incident X-ray radiation from space will reflect off of that rock, and your spectrometer is then able to create a reading that can give you information about the chemical composition of that rock. And it also has a set of RGB LEDs on it. And so we had the Pixel Disco Party the other day as a test activity. I'm not sure if that picture was released to the public, but it's basically the Pixel flashing its RGB LEDs, and that was crazy. Anyways,
Part of robots if you choose now.
Nice.
the point is to illuminate the subject for the observation. So this little ball here is called the GDRT. This is the gas dust removal tool. And on previous rovers, we had the DRT, and we had the RAT, which was the rock abrasion tool. And so this time around, instead of brushing the dirt off of rocks, we have a gas canister that blows the dust off of the top of rocks to give us a clean surface to make observations. So it's not a science instrument in itself, it's used in support of science observations. Over here, we have the Watson, which is a hand lens imager. On Curiosity, it was called the Molly. And the way that it works is you can see that there's a cover on here. The cover opens and closes. When you bring it up close, you can get an extremely high definition imaging of rocks. And that lets us see the structure of these targets that we're looking at, the clasts. And it can also be used for performing diagnostics that we wouldn't be able to get otherwise. Very important diagnostics, such as taking selfies, which you may have seen, our lovely rover selfie that we took a couple months ago. The way that's done is you hold the arm out and you very slowly take the Watson, many images. I don't remember exactly how many images it takes to make a selfie, but it's interesting because engineering camera's role on that is to image the arm while we're taking pictures of ourselves with the Watson. And you can see the way that it's done is that the position of this camera stays the same to reduce parallax as much as possible. And the turret moves. When you see it in animation, it looks quite interesting. So the last thing here that I'll point out is the coring drill. And one of the main reasons why we're here on Mars is to look for signs of past life, and also to study the geology and mineralogy of this very exciting region of Jezero Crater. And one of the unique ways that we're going to do that with this rover that we couldn't do with the Curiosity rover is to collect samples of rock, store them inside of the rover, and have them be collected by a later mission and brought back to Earth for further study. And this will be the first time that we're actually bringing back material ourselves from Mars to Earth. Nothing's ever come back before. Of course, incidental pieces of rock from Mars have landed on Earth before, which is natural due to micrometeorites and those sorts of interactions that you have in space. But so this coring drill is very exciting. We haven't taken any core samples yet, but we will be soon. So that's something to look forward to.
Cool.
And where they go is actually right here. which is where you put the mirror button. I was wondering why that was interactable. So this door here, there's a couple things going on here, actually. There's the big carousel, which I won't get into because it's down in the weeds. There's this door, which leads into the sample handling assembly, which is in this part of the chassis. And where the belly panel was down underneath here, approximately in this area, protecting that. So with that gone, the underside of the rover is actually exposed at that point because we're able to drop the test tubes directly onto the surface of Mars for later collection. And the cool thing with the Watson, in addition to taking selfies, the other type of diagnostic activity it does is we can image underneath of the rover by pointing the arm down and looking under. And there's a mirror conveniently located inside of that sample handling assembly that allows us to look up inside of it and perform additional diagnostics that way, because there's a lot going on in there. There is an arm that some people affectionately call the T-Rex arm because it's a little sample handling arm. And there's also another engineering camera inside of there called the cache cam. And when we present a test tube to the cache cam, we can get a really good quality picture up inside of it. So yeah, that's what's going on with all of that. Oh my gosh, there's so many parts to this rover. I hope I'm not going over time or something.
Oh, it's perfectly okay if it's something you're concerned about. As really, it's awesome hearing you talk about all this stuff. If you feel like you're going over time, you're not. I mean, you go about 15 or so at the moment.
That's
Okay,
all right. We're going by Martian time. Don't worry.
Yeah, Mars minutes. Sounds good to me.
Yeah.
Okay, so I'm gonna get through the last couple things. Luckily, the back half of the rover, from a scientific perspective, is not as interesting. From an engineering perspective, there's still a ton going on here, of course. This is the Metaboom, and this is our weather station on Mars. It's able to perform temperature, pressure, and wind direction and velocity readings, amongst other things that I'm not totally familiar with. And it also has the neat side effect of appearing in a lot of our navcam images, because when we look down towards the ground, this Metaboom sticks out into our field of view. So that's fun. Okay, back here, this guy right here is the antenna that we use for communicating with the helicopter, Ingenuity. Ingenuity doesn't carry communications equipment powerful enough to communicate directly back to Earth, or even directly back to the orbiters that fly overhead. And so this is fairly similar to a commercial receiver for something like an RC helicopter. Well, yeah, I'd need to double check on that. So take that with a grain of salt. But next, we have the EDL cam uplook camera. EDL cam meaning entry, descent, and landing camera. So those lovely pictures that we got of the parachute came from the descent stage uplook camera. Of the sky crane came from this camera. This is the Mastcam calibration target, because Mastcam can take multispectral imaging. In a similar way to SuperCam, however, SuperCam, their spectrometer has much greater spectral resolution, but its spatial resolution is one single pixel of space, right? And whereas the mass cams are a regular camera, but they have a color filter wheel, and so they can put IR filters over the camera to view the world as it would appear in infrared. And so these splotches of color respond differently to different IR color filters, and that can be used for calibration. And this part that sticks up is actually a sundial. And so that can be used for calibrating the local solar time. Okay, so back here, this is our radioactive power source. There's a large pellet of plutonium inside of here, and the heat that that plutonium generates can be converted into electricity to charge the onboard battery. And that's how we get our power. So with operations, it's a balancing act of what you want to do versus what you have the energy to do, which I think is true of a lot of things in life, actually.
Yes.
And so sometimes if we don't have enough energy, we have to wait for the battery to be recharged slowly over time by the RTG, radioisotope thermal generator. Now, conveniently located right next to the RTG are our two rear HazCams. These are basically like our backup cameras, and they're also engineering cameras. And I think they're lovely. However, they have a slight noise problem compared to the other cameras on the rover due to being located right next to a rather large radioactive power source. But that's okay. The image quality is still very good. But what can happen with these types of things is that even a little bit of radiation noise in your images can reduce the quality of the stereo data, especially when heat becomes a factor. These cameras stay consistently warmer because they're next to something that's very warm up here. The rest of the rover gets quite cold when it's not being directly heated. Okay, so yeah, that's the rover. There's other parts. I could tell you all about the antennas, but I don't know how many antenna nerds there are in here. Want to hear about X-band communication, so I'll skip that part.
Okay.
The next thing I'll talk about, I guess, is where we actually are on Mars. It doesn't look like this, but this does look like Mars, or fairly close to what Mars looks like. So the representation of the environment is quite good. Jezero Crater, and the reason why it was selected is because it's thought to, like, if our mission is to look for signs of past life, then that spot is a good bet if we're going to find it. And the reason for that is there's what's called an alluvial fan formation. You can find these on Earth. What it is when you have a river, especially a seasonal stream, that flows through a valley, it creates, a trench over time, or a channel for the water to travel through. And if that water suddenly goes from its trench to a wide open flat space, then it will spread out across that space. It kind of would look like that right over there. So you see, or that one, like, see how there's those two rock formations, and then there's like the sandy, silty stuff in between that flows out in a bunch of little channels. That is not exactly what it would look like, because that is more of a flowing sand type of situation. But if you look at the satellite imagery, which I have in a presentation that I gave a little over a month ago, you can see the way the delta formation looks like, your standard channel of water spreading out over a dry, flat plain. And so that carries, well, first of all, it points to evidence of past water, right? It's not a guarantee, but it's something we can be quite confident about. And then the other thing is it carries sediment from a lot of different areas. And so those other sediments increase the likelihood of finding evidence of past life. And it also increases the geological interest of the region. If there's a lot of diversity of rocks to study, then we have happy scientists. And I am not a scientist. However, a lot of my work revolves around providing data and acquiring operations that enable scientists to do their work. So yeah, that's very important. Our day-to-day operations involves studying different layers of rock in this region, and how there are micro changes, like there might be a couple of interesting clasts here and there that we want to study and be like, well, how did those get there? Because they're quite different from the bedrock around them or the sediments around them. And then there's the macro changes, like it's a lot easier to see on where Curiosity is, which is Gale Crater. Gale Crater has a large mountain in the middle of it, Mount Sharp. And we are traveling up Mount Sharp. We're on the edge of it. And there's several exposed stratigraphic layers in there that have markedly different compositions. So that's very interesting for scientists to study, because if you see, for example, high levels of hematite, then hematite is often associated with past water. And so, we went and studied a ridge that was raised up from the rest of the valley floor that had a high hematite content. And the areas around it had different types of rocks. And so, in general, our operations ends up following this cadence of different campaigns. When I started working on Mars Rovers, for example, one of those campaigns that I worked on was the Bagnall Dune campaign, where we were coming from, we passed the Murray Buttes, which was sort of like our entryway into the foothills of Mount Sharp. And from there, rovers don't like to drive on sand. And there was this big belt of sand dunes for a long way in either direction. And one bridge of bedrocks across those dunes. And so we passed through that bridge of bedrocks to continue on our way, ascending Mount Sharp. And along the way, we were able to study the sand there, and there was also a little hill, Ireson Hill, that was kind of neat to study. Nowadays, after the ridge and the Greenhue Pediment, they're heading towards the Geddes Vallis, and there's very, very tall buttes now that we're seeing, upwards of, I think, like 50 meters tall, which is a nightmare for communications, because you like a wide open field to communicate with the orbiters. In Jezero Crater, we've kind of been heading south from where we landed, and Originally, we were studying a region called Seta. We still pretty much are. If you look at the satellite imagery, which publicly available. Yeah, because actually, if you like maps, there's a website called mmgis.jpl.nasa.gov. And that is like Google Maps for Mars. It lets you look at top-down maps of where the rovers are. And you can also do various overlays. You can measure things. And you can see the path of where we've been. It's pretty fun to play around with. It's very, very similar to the tool we use in actual operations for our maps. There's, of course, other tools, like we have a 3D model viewing tool, and we have tools for targeting and so on and so forth. No VR tools, unfortunately. Although I have brought it up. I've been like, hey, can we have funding? Can we have funding?
Videos. Yeah. So
it's been discussed before, but yeah.
If I may, first off, I want to say that right now we are running a bit short on time at the moment.
Sure.
But the rest of the time, I think, is going to be dedicated towards questions. So we'll have about 20 minutes or so questions. I'm sure there's probably a lot. And so I'm sure that a lot of people are probably going to bring up a lot of very interesting questions. But I'll say we got to keep things, obviously in respect of other people who want to ask questions, because we want to keep within that 20-minute timeline, you know what I mean? So we don't want to kind of keep it over.
So no follow-up questions.
Precisely. No follow-up questions. Just ask your question directly, and then, pretty much you can go back and then that question will be answered. We'll go on to the next person. We'll try to do this pretty systematically so everyone can get through in a timely manner, as I know there's probably a lot of curious individuals that want to ask some stuff. So first off, how we're going to handle this is if you want to ask a question, I want you to kind of like line up right here next to me, right here, directly to my left. Yes. Come on over there. Just this nice single file line right over there. First come, first serve. And I'm going to cut it off whenever I can. Hug, you can just message me your question and I will answer it for you. Okie dokie. Yeah, if you're a mute, just go ahead and message me the question if you have it, or if you're in the Discord, you can also add me if there's a mute. I believe there's a chat in there that you can just add me at in the general. Just wave in my face. You send me a question, okay? Awesome. So that's 1, 2, 3, 4, 5. Okay, so that is 5 questions. Do we have anyone else going once? Going twice? All right, that's it. These are our questions. Go ahead, Evolved Ant. Ask the first question.
Hello, I'm Evolved Ant. So my question is, I was curious, what is the logic that is used, that NASA uses to determine which photos are released to the public and which ones are held back?
So we don't actually hold photos back. We do delay the release of the processed images. However, all of the raw images that we acquire are released to the public pretty much at the same time as we get them. And so sometimes, actually, it's been the case that members of the public, like I've seen a picture appear on Reddit and be like, what the heck? Like, I was just about to assess those images and somebody already posted it on Reddit. Because the difference is like a couple minutes, honestly. For the processed images, it gets kind of complicated, but basically it's because the scientists need to use those images for writing papers and doing research and stuff like that. And so they don't want members of the public beating them to the punch on those scientific discoveries. And so usually the images are released about 90 days. The processed images are released about 90 days after they're originally created. And they're actually reprocessed to be as clean as possible. So yeah.
Cool. Thank you very much.
Awesome. Thank you. All right, Joker, go on ahead. Just keep in mind, just keep it to where the question can be answered in a pretty short time frame. So go ahead, Joker.
Mhm. Cool. Jackie, thanks for coming out. This is really cool. Thanks for talking so much at us. You got me curious about temperature when you were talking about the power plant. And I'm wondering how much time do you have to spend worrying about and managing operating temperature of all of the devices that you have to manage? Is the cycle of the day and how much sun it's getting, does that matter in air temperature? Do you have to worry about that? It's how big of a deal is that?
It's a pretty big and constant concern, and luckily we have an entire role in operations dedicated to that. So there's a thermal role, and those people are responsible for creating what are called heater tables. And they tell us, based on the expected temperature at that time of day, at that time of year, are we going to need heating to operate whichever instrument we want to use. And so it's able to determine how much heating using an automated algorithm, which is very simple actually, because it's just measuring the temperature and waiting until we reach that set temperature. But we're keeping track of the allowed operational ranges of temperatures for every instrument. For instance, for our cameras, we're not allowed to operate them below minus 55 degrees Celsius. And there's a lot of reasons for that. But basically, electronics on board don't like to run when it's colder than that. And we do get down that cold overnight. So, each instrument is responsible for making sure that their instrument does not operate below its minimum operating temperature or above its maximum operating temperature. So yeah.
Awesome. Thank you, Joker.
Also, high five.
High five. Nice. All right, Frozen, go ahead and ask your question.
Hey, Jackie. I'm actually in a Discord call with a couple high school kids I actually mentor. I'm a software engineer, so they've been asking a bunch of questions, and we voted on the question that we wanted to ask you. Sure. His name is Tony. I will eradicate his last name. His upvoted answer was, I'm extremely interested in engineering. You've been mentioned that you got into engineering with NASA at 20 or 26 now. What brought you to working at NASA?
Well, so that's a very good question. And my best advice for high schoolers in that regard is to not stress out too much about what your major is going to be, or what specialization within that major you're going to take. Because the best way to learn about getting into engineering is to try different things. When I was in school, I actually picked my major, which was electrical engineering, because it was the best funded department at the engineering school. And I said, well, I don't know if I like electrical engineering, but I'm going to go where the money is, and maybe that'll work out, maybe it won't. And initially, I was working on 5G research, and I actually did not like it at all. It was very stressful and a little boring, and it just wasn't really for me. It wasn't a good fit for me. And luckily, I was able to change focus to learning more about image processing. And I found that I really clicked with doing image processing. And I was able to get a few projects under my belt doing that sort of stuff. And so when I applied to an internship at JPL, I was very surprised to learn that I had been accepted. And so, yeah, my first internship, I wasn't been working on spacecraft. I was working on software for viewing data coming off of spectrometers in real time. Oops, I just moon jumped. And then I reapplied, and the rest is history. Yeah.
Very cool. Thank you. Thank you so much.
Amazing. Alex, go ahead.
Have you ever brought up to any of your workmates or friends at work and thought about using VR actually as a way to do some of that work?
Yes, and I think I've probably annoyed them about it. Because
Jackie.
well, so a little before the rover landed back in February, I was actually able to convince one of my team members to come in here and help me give a presentation in a very similar world. And she said she had a good time and that it was interesting. Yeah, and I've also talked about, the potential applications of VR. There have been projects, like I said, that I've been working on, but it's still a work in progress. I think one of the most promising projects is being led by a woman, Sasha Samachina, who she makes her software is called, I can't remember the name of it right now. Oh, that's so bad. She also worked on a lot of the iOS and Android apps that you can use for viewing, like spacecraft AR, if you've ever played around with that one. But yeah, her big project lately has been an augmented reality spacecraft design software. So it lets you view components and entire models in a shared augmented reality space using the HoloLens. And prior to that, there was a team working on a tool called OnSite, which actually enabled you to go to the surface of Mars and look around and move around and stuff. But it wasn't augmented reality. So, yeah.
That sounds hecky cool. Thank you, Alex.
Yeah, really cool. No problem.
Augmented in reality and VR, man. Doing all the cool stuff. So let's hope that one of these days we can get we can just slap a whole
there are
headset on
plenty
this
of NASA created VR experiences as well.
Let's go. Yeah.
Sparky.
Yep. Let's go, Sparky. You got your question? Let's go.
Oops.
All right. So, yeah, my question is about the SuperCam, and it's pretty simple. The range of the laser. What's the effective range? And if you're operating it at maximum range, does the procedure for gathering data change? Is it like any different or what?
Okay, I am very bad with exact numbers. However, I will say I worked on a little piece of image processing software back during when I worked on Curiosity that was trying to think about this exact problem. So for the laser, I think its maximum range is somewhere around like 5 meters. Don't quote me on that. Definitely less than 10. Actually what can happen when you're too close, at least on Curiosity, I don't know if this is still the case on Perseverance, because I haven't looked too deep into the technical documents of the instrument. The energy from the laser reflects back a certain amount into the SuperCam hardware, or the ChemCam hardware, as it were, on Curiosity. And when we're too close, that energy can be so great that it could actually damage the hardware. And so there's certain no-go zones for targeting very close in, where the reflected back laser energy would be too much. And so generally there's a sweet zone that's especially good for using the libs.
Okay, yeah, that's what I was curious about. Thank you.
Awesome. All right, Don, final question. Well, second to last question.
Yeah. So my question was, you mentioned earlier how the rover uses two CPUs that have the same computational power as from the early 2000s. So my question is, why were there CPUs on there that were, 15 to 20 years ago being used? Was it because it's more robust? When they land, they're less likely to break or cost effective, or it just kind of surprised
That's
me.
a
I mean,
really good question, and I'm sad that I didn't get to go into it in more detail during the actual presentation. So for the RCEs themselves, and also before I get into the RCEs, I just want to point out they're not our only processors. So only one RCE is active at a time. One is backup. They're called the A and the B. But then in addition to that, we have a number of co-processors. And so there's onboard flash memory. We also have a number of storage devices associated with each instrument. For instance, our onboard memory is only a couple of gigabytes, but then some of the instruments, like EDLCAM, have several hundred gigabytes of storage. So why do we use some pieces of hardware in some situations and use quite old in terms of their processing power piece of hardware in other situations? The reason is reliability. When you're here on Earth, and first of all, we're shielded from radiation by the magnetic field that surrounds the Earth. We don't have that same protection on Mars. And so you're constantly concerned about radiation flipping bits on a spacecraft. And those are called single bit errors, or it could be a double bit error, or it could be a single event upset. And if it's a single bit error, then it's easy enough to just flip the bit back using error correction code, ECC type memory, which they use in computers here on Earth in high reliability situations. Double bit errors get a little more complicated. The special thing about the RCE is that it is certified to a certain degree to be resistant to radiation more so than your average computer hardware component. That's called rad hardening. And that costs hundreds of millions of dollars. And so the process to certify a component as complex as a CPU to be rad hard and have that level of reliability where it will work for decades without fail is very difficult to do. And so it only gets done every so often. Whereas, the VCE, which is the vision compute element, which is used to help us process images when we're driving using the auto navigation algorithm, is much faster. But it's not guaranteed to be as reliable. And if it fails, then we have a fallback in the RCE. Similarly, the EDLCAMs have their own coprocessor, which is very similar to something that you could just buy off the shelf. But when you throw something like that in space, they only plan for it to last like a week, Yeah. Luckily, it's still kicking, and, it's been offered to be used for some co-processing capabilities if we need it. But, it's not certified for doing the same types of activities as some other types of things. Sorry, that was a long-winded answer, but it was a very good question.
Thank you. Because it was the same question that Hug had, actually. So
cool.
You
so that's why
actually
you were
answered
like...
both. Yeah.
Don't worry,
I took
Hug.
a picture of them because they looked really interested. They looked like you should have seen their reaction the moment they heard the question. Like they got so attentive. I had to take a picture of it because it looked. All right, so I think that's going to do it for the questions. Now, without any further ado, I believe the map makers have something to highlight the end of this event for a little bit of something fun. I'm not going to spoil what that fun thing is because I think it's really cool. And we're gonna hop over there right now. So if the map makers could take it away and show us where this really cool thing is, Jackie, I need you to stay behind, and we can show you the fun thing later. I need you to talk with Conk real quick if you can. Which Conk, can you come over here real quick? And everyone else, map makers, take them away over
I think we're
there.
in trouble, Jackie.
I actually have a request for
I
you,
guess.
little
Someone
bagel.
better
Do you
get
think
it.
you could drop a new portal to this world so that people can join off of you?
We drove
Because no one's
around
been
quite a
able to
bit
rejoin
earlier.
because
Oh yeah.
Okay. Cool. Do we have where'd John go?
John is coming. I think.
Oh, okay.
I think John is coming.
Space.
All right.
Space.
I don't want to steal
The
his
final
thunder.
frontier.
You can talk about Slow Rover if you want, Dylan, while I get
Okay.
John.
Accurate, Percy. So this is we affectionately call this Accurate Percy, because this is the rover that moves at the accurate speed. So the actual speed of the how the rover moves, and you can. I think it was John knows the actual number, and I can never remember what it is. But yeah, 0.1, is that it? Okay, thank you. Yeah, so this one moves at 0.1 kilometers an hour. So if you want to jump in, if someone wants to test it out, you can hit ride here and show us all what Accurate Percy does.
Oh, very nice, very nice.
This
slow.
is awesome. This
This
is
is
great.
amazing.
Hold on, I got this.
I'm gonna beat it.
Oh,
Who's
please
gonna
don't
win?
run over me, for God's sake.
Got this.
Oh no!
I just realized what movie scene this is.
Oh, you're talking about Roger Rabbit?
also-
Oh, God, it's getting closer.
Yeah,
Okay, good.
Who Framed Roger Rabbit? That one scene with the
Yeah,
funeral.
Who Framed Roger Rabbit. Yep.
This is also the
So-
max.
I'm thinking
speed
of Austin
rover.
Powers.
It actually
Oh, the
travels
max speed, yeah.
slower
The
than this,
max
but
speed.
yeah.
John, was there anything else you wanted to say about it, or?
Oh, sorry, I just got here.
Yeah,
You-
I was just
you
saying
pretty
the
much got it.
accurate Percy. Yeah.
Oh, did you talk about how to ride and such?
Well, someone just demonstrated it.
Yeah.
I think people figured
I
it out.
think they
got
figured it out. Yeah.
That
So
could
then we
have
got
been
these ones
hard.
over here that are the racing ones.
Yeah.
Yeah.
So when you click
Basically-
ride, you do grab the
Yeah.
steering wheel and use your
Right.
triggers.
God.
You will see
Yep.
your velocity while you're on there. You can also click on settings or setting, and you can change where you sit, depending on
Okay.
if your avatar likes where it is or not. You will
Very
notice these
useful
ones
if you're short.
go a lot faster.
Oh, hold on, hold on.
Woo, go
Oh,
for
yeah.
it.
There's a right button
Oh,
on
that's
the
nice.
outside. You can hit this button right
These
here.
things are hauling.
Ah, right. Okay. All right.
And we also made it so that the sound,
hi.
the revving is
Oh, no, there's no horn.
changes
I
with
like
the
that.
speed.
Yeah, I like that.
Oh, you want me?
Yeah.
Oh, no, someone's on. Sorry.
I mean,
Oh, no.
You whippersnappers, come
I'm
back
glad I
here.
don't have to worry about noise complaints.
Is there a horn?
Yeah.
Cat, stop it.
Yeah. Horn. Where's the horn?
We're at, like, that what you're asking? Is there a horn?
I mean, the air's thinner on Mars, so it
The
sounds
It's
horn-
just like the
I will have to deal with cats.
Been here for 5 minutes
don't
and
really
it's been an
travel
hour.
through this air very well.
Exactly. Has
That's
to be like
really
a
that's
bass
this is an art
of those
project.
sounds.
You know, this kind of reminds me of when cars first came out and people thought their heads were going to blow off when they were going 10 miles per hour.
What?
Because it was so
Yeah.
fast.
Watch where you're going. Jeez.
Oh, God. Logan, hey, do you have Martian insurance? I'm going to sue you. I'll see you in court on Tuesday.
Nationwide is on your side.
Amazing. Knew Mars would be so
This isn't a nation, it's a planet. This is a planet.
NASA.
It's a whole planet.
True.
Like, ever since I was in elementary school, I've been interested in space and engineering and just in general.
Hey guys, I got some bad news. I think my rover's defective. It's not going as fast as all the others.
Oh, thank you so much. We really enjoyed making it.
My batteries are getting low.
I think so.
Oh my god, that was a question I really wanted to
No.
ask. I was like, do they think that they're gonna find Oppie at any point? I really want to know. Like,
I think NASA would have saved a lot of time and money
launched a rover to
if
Mars
they just
in the
sent the
70s,
rover
they
to Area
still haven't found
51. I think they might have found life there.
yeah.
Really?
That's true.
Oh man.
Is that true?
Yeah,
Like
like
six-
there.
That's not
Yeah.
true.
Yeah, it is.
Yeah, but
Really?
so the
So
Super Cam, I think it was like
Like a
1972.
rental car instead.
Yeah,
Did
well,
you
they
get
could have
burned
been
up
one
in
of those
grassland? Yeah, they did.
No, that
Yeah, the
that
Soviets, they actually did a lot of things that
Earth
most
one
people
at
don't
this
know
speed.
about, but
Yeah.
like the big thing was America landing on the moon, which is great and all, but in terms of first satellite, first animal,
We need to
first
spend $1 billion
cosmonaut,
to make a rental car
first
that's much
probe to the
smaller
moon,
to find.
and first probe to
that's a lot.
Mars. I think
Area
that
for
was
doing.
all the Russians. Yeah.
Yep.
Wait, how far have I gone? Hold on, I'm gonna make a hard U-turn. I'll be back to start in an hour.
A hard U-turn.
Stop. They think you
Yeah,
stop.
look at this.
They
Look at
don't
this
know.
bad
You're
boy go.
You're still moving.
Oh yeah, you're going right around.
Oh man. Oh my
Somebody
god.
ran into your back and did a flip.
Oh my god, what's going on here? Hey guys, this isn't bumper cars. If you ram the back of this thing, the plutonium's gonna go off and kill everyone. Okay, calm down.
Yeah.
Jeez.
Yeah, seriously.
No, don't rupture the plutonium core.
Look at this. It's already a pile up.
Beep.
Oh boy, can I do this on desktop? Let's see.
What is this? Wait, is this picture actually on the rover?
This
right
is the
here?
gnarliest donut I've ever been part of my entire
Ooh, I
life.
can actually drive this. Sweet.
Hi. Don't mind me. I'll be done with my donut in about an hour.
Excuse me,
I'm just
I
gonna
need to
keep
get
going.
through here, sir.
Well, you know what? Maybe if my plutonium wasn't low,
I have an appointment to
that'd
make.
be good. You have an appointment to make? Well, I'm gonna cancel that
and
appointment.
You're blocking my.
Look, I'm going as fast as I can. Okay. I'm
Hit the
telling you, this
pedal
thing
on
is
the right.
this thing is
You want me to
defective.
push? Hold on, I'll give you a push.
Yeah. Hold on. Oh, I think you broke something. It's not moving anymore. Oh no, wait, we're good. Okay.
You good?
We're
We're good? Okay.
Yeah. I
I'm
thought
literally
something
doing
broke.
circles around you.
They were making
I'm just
a joke.
I'm just
They were
making a really
joke.
wide. I'm just making a really wide donut right now. You'll be able to see it from space. It's gonna be awesome.
This is fantastic.
Yeah. I got this.
Yeah, absolutely.
There we go.
Yeah, being friends with Carl for so long, I've broken.
Oh, you can't just go circles around me like that.
I am. I'm literally doing circles around you.
I'm literally going circles around you.
And it's
The
great.
rover sucks.
I'm about to run. I know, man. It's just I don't know.
That's pretty awesome.
I don't know what's wrong with it.
Well, I hope Jack
Find the next gear.
will come back.
I think there's
Come
only
on.
I think there's
For
only
family,
two.
Don.
Forward
For
and
family.
backwards.
Yeah.
For family.
For family.
Weird not having.
That might seem a joke actually. So how many gears does an Italian tank have?
Yeah, I was gonna say for
How many?
One forward and three in reverse.
Super flat.
Whoa!
Wow, this is so fitting.
The one that I found first, but
That's amazing.
it's close enough.
Yeah,
My God.
blame Melty Bits. They hit the creeper.
You had me so
Hold on,
dumb.
I'm
I'm
gonna
like,
drive the
I
rover
didn't
into there.
program in explosions. What the hell?
Oh, that's actually pretty cool.
That's just
Oh my
called
God,
bad
secret
code.
Decent job.
Mars.
That's bad code.
No!
No.
Well, I'm glad we made them fun.
Oh fuck! Oh
I
fuck!
cast
Oh, fuck,
slap
fuck.
explosion.
Every time.
And in
At least I have room to move around.
It's also
No?
just like fun to hear people
Just
who've
I can't
actually worked
fall
on it
because
talk
if I
about,
fall,
like,
it'll be a
stuff
hard
on the
fucking
rover.
floor I'm landing on.
Yeah,
Yes.
totally. Yeah.
Or an uncushioned couch.
I love hearing people who are passionate about things that they've worked on talk about them. Yeah.
Oh yeah, I love that too. It gives me like this weird tingle in the back of my
Oh my
neck.
God, you're still
That's
doing
how
this?
I know when I'm like, I can't leave a conversation.
You're done before you began.
Yeah, this was an event. We were
Look, this is
Here-
art. Art
there
takes
was
time.
someone.
Made before, I'll listen. You know.
Quote unquote art.
There was one of the engineers at
Okay,
NASA
fart.
that works
Okay, what's the
with the
difference?
rover that was giving a whole
Fast
presentation
fart.
for us here.
Yes, that's exactly what that means.
But it's the end.
Must give pats. Must give pats.
I should have set
Okay.
my status so people could know I
Thank
had
you.
so many people requesting off of me.
You're welcome.
Oh God.
Wow.
We need theme music for that, right?
Every
We need that.
time with you.
I thought about updating the
Yes,
photos, but I'm
that's what Hug
Oh
does.
fuck! Oh fuck! Oh fuck!
something to say about all the photos that were there. there, so I'm like, oh,
Right.
yeah,
The hell?
change them. So.
Look at this, Dawn. You're crawling along at 0.1 miles an hour, hugs bouncing on 1 foot.
Whoa.
While driving this thing at like Mach
Excuse
3.
me, sir. You need to slow down. You need to slow
Can't,
down.
I've lost control. Oh God, get out of the way!
Oh my god, he's out of control. He's
I'm out of control.
Oh my God.
Get out of the way! I'm out of control. I can't stop this thing. It's going too fast. I can't.
Actually, hold on.
I can't stop it. I can't stop it. It's
1 mile an hour.
It's just this trajectory. No, what are you doing?
Oh my
This
God,
isn't
Ann,
funny.
move,
Get out of the
move,
way. I don't want to kill anyone. I've lost control. Jesus, take the wheel.
No.
Eject!
Oh. Yes.
I hit the eject.
Madman.
Oh, red.
I did it.
Look what you did.
Oh no!
Panda.
I will finish what you
I'm
started.
blaming the Martians. It totally wasn't the Earth people.
Every
I'm blaming Matt Damon as the dragon.
Blame Matt Damon.
Hold on, I got
The
this.
Mars Rover massage.
This is not the acupressure I asked for.
Oh, this is great.
Free massage on Mars.
This is very good.
It's an outline. That's great.
How'd you get that? Oh, that's neat.
Oh my god.
That was great.
That would be great.
Oh wow.
Oh, wow.
Laugh is true. Laugh.
So this is what Mars is like. Okay.
At least there's
Oh
food.
my god, the dead body.
True. You'll last us for a year.
Oh no! I didn't realize you were talking about me.
Yes. Yes.
Can you go blast? Can you eat the mustard side first? I'm not a fan of mustard.
I'm not a fan of mustard either, so we're gonna have problems.
Oh.
Oh no.
Best meats in
Oh
the
no.
world.
Here, we'll just scrape the mustard off, and we'll give it to Yas. Yas, you like mustard, right?
I guess.
Yeah, that's good enough. Sweet.
Oh, mustard. Hold on, I'll be right
Right.
back. I'm gonna go get some.
Hold on, are we in our suit outfits? Hold on, I have an Among Us
Vince.
You can have
monster.
mayonnaise. You can have mayonnaise on your hot dog instead. Is that better?
No.
That is so cursed.
What
Yeah.
the?
No.
Excuse me?
You just ruined a hot dog, is what you've done.
Sprinkles. With
Mayonnaise is not
What did
gonna